Welcome to the second part of the CEST sources tutorial about CEST MRI data evaluation. So this time we want to concentrate on the Lorentzian fitting of C spectra and like pixel-wise fitting. So if you have just performed the same evaluation as in the first tutorial, so it's the same package, so just add the package to the path, all folders and subfolders. Then load your CEST data, create a segment, do your B0 correction and normalization, save this stack, and you can have a look at it with an image user interface. And now we come to this fitting part. So let's have a look what happens here. We have this fit options. That's actually a max file. It's a compiled C++ file that fits this spectrum using a Levenberg-Marquardt algorithm. And here you can give the iterations and some stopping conditions for this algorithm. So we use 50 iterations here, which performs already quite well. And here you can set the model number. So we have like different Lorentzian models, like multi-Lorentzian. You can choose from 1 to 5 and even create own models. And like one would be a single Lorentzian file if you just want to fit the water line. And here we use now a 5-pool Lorentzian model. And if you choose this, you will automatically get a fit which is optimized for low power C spectra at 7 Tesla. And if you want to directly change the options, you can set this variable pfit_ext_opt to 1, and then you can create the lower and upper bounds of the fit directly. So these are 5 Lorentzian functions here. Yeah, the Lorentzian function is defined by the amplitude, the width, amplitude A, width G, and the offset delta omega. And so we have first the waterline, like we have a constant offset here where you can model the not fully relaxed state. We have the waterline, then the amide peak, the NOE peak, a broad semi-solid MT, and the amine peak. And these upper and lower bounds you can adjust. So for example, the semi-solid MT has a very broad line shape. Yeah, so it's a very broad line between 10 and 100 ppm with a starting of 25 ppm. And here's the position of the amide peak. So for example, here you see the 3.5 ppm of the amide protons. This is stored all in the parameter struct P. And now you can run the fits. I added again this segment selection, so if you run this now, we get again asked to choose a segment or region of interest. This is just to speed it up a little bit, so let's pick a quad of the brain now, for example. Then you can quickly test your fitting algorithms if the fit fits, and and all is stored in this popped, the optimal parameters. And there we go already. So these optimal parameters are just given here. So that's the initial magnetization and then the different Lorentzian parameters. For example, let's have a look first at the water line. So this would be the peak of the water line, and we see it's not so deep because of the broad ME. It's not so deep in the white matter. Therefore it's dark here, and it's brighter in the gray matter region. And now if you click here, you see the data together with the fit. And that's actually quite nice match. So you see here, the Lorentzian does not perfectly fit to the NOE, for example, but overall also in the MT range, it's a pretty good estimation. Also the waterline is fitted nicely. And you see the amine peak and the amide peak are nicely fitted here. And now you can just click around and see how well your fit performed. You also see the isolated peaks here. You can click to peaks at bottom to isolate them a little bit more. So we see the water peak, we see the broad MT peak, we see the NOE peak, amines and amides. And now you can just click around and have a look, okay, how well is this model? Yeah, and it fits quite well everywhere in this area. Yeah, now you can pick the individual fit parameters, like the waterline, but for example the amide peak now. And if we look at the amide peak and scale it a little bit, we see, well, there's not too much. There's a little bit noisy and seems to be quite low effect in white matter, but it seems that gray matter has a stronger effect, which was also reported before. But you can really click in these hyper intensities now and check what the fit actually performed. And let's have a look at the NOE. Yeah, that's a typical NOE image with a stronger NOE in the white matter and a lower NOE in the gray matter. You also see a part of the liquor here. So let's have a look at the whole brain. The fit was already performed in this example fit file. If you just load this and run the im GUI again, you can just have a look at the amide map of the whole brain and just inspect the gray and white matter contrast if you want. Or let's have a look at the amplitude of the NOE Lorentzian, which looks like that. So now the next step would be what we did before with the asymmetry, to check this linear difference and the inverse difference and the AREX. And for that I want to explain you quickly what happens when we create this C label and C reference. So if you look at the neuroimage paper, there it was described, the relaxation compensated CEST MRI in human brain. There you see in the methods section how this reference scan and this label scan is created. So we take the label scan, which is the actual C spectrum, and from the fit we take one Lorentzian and, for example, the amide or the NOE, and add this to the C spectrum. And this creates our reference C spectrum. Then of course, again, if you do the linear difference, this is exactly the same as the Lorentzian amplitude. But if you want to create an inverse difference, we can now perform this with this reference and label values. Yeah, so to check this, let's have a look at the A2, which would be the NOE, right? So we can also pick the NOE here, pick linear difference, and this pretty much looks the same way. We still have the freedom here to go through the offsets, because this is really the amplitude and this is the amplitude at a specific position. But with this now we can investigate what happens if we do the inverse difference. And as you can see here, the effect in the white matter actually increases because there we have a strong MT and these effects are diluted, and the inverse metric removes this spillover and MT dilution. And if we go for AREX, we see that the contrast stronger improves and we have a very strong gray-white matter contrast. We can do the same for the other peaks, for example amides, linear difference. We get pretty much the same image as before. If we do the inverse difference, the contrast changes a little bit. We still have like more intensity in gray matter, but also in the central areas we have now a larger signal, which might still be due to the high B1 in the centrum. So, and if you look for AREX, we actually see a very strong effect in the center, and the gray matter contrast is now much lower because this long T1 actually artificially increases the CEST effect, but this is maybe just because we have a long T1 and not because we have a very strong CEST effect. But still we see some gray matter hyperintensities. That's pretty much it. So with that you have a tool, and if you want to go further with this evaluations, you can also directly access this C label and C reference and create whatever there. If you look at the C reference scan, you see that these are actually multiple arrays, like a reference for the amide, for NOEs, MT, amide. There's also reference only the water, and the reference background, which is actually MT, NOE, MT, the baseline, and the water. If you want to have a look, just look into this function and look how these are calculated. Yeah, this get fit label reference. Yeah, and with that I end, and well, now you can perform this for different B1 and just reevaluate each stack, and then make ROI evaluations over B1, over pulse duration, or whatever. I'm happy if you use this example data. Maybe this is a good start to combine some different evaluation methods and compare them very nicely. So that's it, and thank you very much for listening.